To answer this question, astronomer Michael Brown and his colleagues followed a procedure similar to the method designed by Tombaugh. But they took advantage of new technology to make their search easier and more effective. Like Tombaugh, Brown's team takes repeated images using a telescope. Every 3 hours, a digital camera mounted on the Samuel Ocean Telescope at the Palomar Observatory in California snaps a picture of the night sky. A microwave link allows robots to control both the telescope and its camera. These robots follow a pre-programmed routine that moves the telescope and takes pictures. This automated system drones through the night while the astronomers sleep. Instead of using a blink comparator, Brown's team sends the images to a bank of 10 computers at the California Institute of Technology, CIT. The computers superimpose images taken at different times and identify objects that are possibly moving. Then the team analyzes the data to try to verify the movement. Most of the time, the objects identified are not breathtaking discoveries. They are simply the result of flaws in the telescope's camera. But sometimes, the computers do track down moving objects. Airplanes, satellites, and asteroids have been flagged by the system. And in 2003, the team discovered a bright shape that was moving more slowly than anything documented in our solar system. Could this be the object tugging on Uranus and Neptune? 1. A 161 megapixel camera mounted on the telescope. 2. Multiple images of the night sky. 3. CIT computers superimpose images. 4. Astronomers Mike Brown, Chad Trujillo, and David Rabinowitz analyze data. Ocean Telescope, Palomar Observatory. Combining new data with old. The super slow speed of this object, which was eventually named Eris, posed a problem. Brown calculated that Eris takes 560 years to orbit the Sun. So it would take many years to collect enough data confirming the deduction that Eris affects planetary orbits. Rather than waiting, Brown decided to check photos taken by other astronomers. Luckily, Eris appeared in photographs taken as early as 1950. By combining these images with contemporary data, the team developed a more complete view of Eris's size and movements. The team originally estimated that Eris was 25 to 40% more massive than Pluto. But when they used pictures taken by the Hubble Space Telescope to confirm this hypothesis, they found out they were wrong. Eris is only slightly larger than Pluto. The overestimate was the result of Eris's extremely reflective surface. The bright, reflected light gives the impression that Eris is more substantial than it really is. Brown suggests that an atmosphere of frozen nitrogen causes Eris's high level of reflection. As a result of Brown's discovery, astronomers reconsidered the definition of a planet. Ultimately, both Pluto and Eris were classified as dwarf planets rather than planets. But discoveries in the Kuiper Belt continue to sustain great interest. Conservatively, astronomers predict that new technology will allow them to identify several more dwarf planets in the Kuiper Belt. The information gained from their investigations will enrich our understanding of distant objects in other parts of the galaxy as well. The Moon, Earth, Pluto, Eris. Relative sizes of Earth, the Moon, Pluto, and Eris.